Hey everyone, I'm Steve with OpenZeppelin. Today I'm walking through the Oracle Market, a Sui reference build marketplace that shows how to compose Oracle price settlement using capability gated admin and phantom type receipts, all leveraging the new OpenZeppelin Math Library as an example of the libraries and Move Lego blocks to come. I'll provide a high-level walkthrough, but for those who seek more details or are newer to Move, check out the Move docs, our docs, and of course this repo for more details. And with that, let's get into it. Here you can see the UI, where you can select different shop objects. You can toggle between localnet or testnet. Right now, we'll leave it on localnet. Each shop is an on-chain object where everything is priced in USD, and the buyer pays in whatever currency the shop has registered against a Pyth feed. In the example repo, and thus this app, that's Sui, USDC, and onward, for example. If you use local or testnet, you'll be using a mock or an actual price feed accordingly. When a purchase completes, the buyer walks away with a receipt, an owned object at their address typed to the item they bought. Owners run the shop through a capability object. Next, let's go through the architecture of the project. Here's the shape, and it serves as an example of how a production Sui app can look. One publish move package with 5 modules, plus one external OpenZeppelin dependency for the safe integer math. The app is composed of a 3-layer workspace with move contracts at the bottom, as you can see here, TypeScript orchestration composing the PTPs in the middle, and a Next.js UI on top. Let's talk about the object model and ownership for the app. Authority lives in an own shop owner cap at the owner address. It gates every admin call. Shop state lives in a single shared shop object, and inside it sits 3 type tables for listings, accepted currencies, and discounts. The Pyth price info object is a separate shared object we read by mutual reference during a buy. And when a purchase finishes, the buyer comes away with a phantom type shop item, which is an owned object at their address that persists independent of the shop. And with that, that's the entire model. So let's start looking at some code. As mentioned, an external dependency is used and can be seen in the move.toml file. OpenZeppelin Math does the safe integer arithmetic with explicit rounding, direction, and overflow handling. The layout of the repo is exactly the way shown in the earlier diagram. Move modules at dap/contracts, TypeScript orchestration in domain, and dap/src, and of course we have a UI folder. The 5 modules I mentioned all live within the dap contracts, Oracle Market, and sources folder. And with that, let's walk through some of them to get a better understanding of what's going on. Let's start with the shop module. Here you can see the one-time witness pattern. Shop is a struct with only the drop ability, named the same as the module. That's the convention the runtime looks for. At publish, the runtime invokes init exactly once and hands you a witness instance nothing else can reconstruct. From there, claim and keep then turns it into the publisher object. No initializer guard required. As for how the shop files are managed, the shop owner cap is used, where it has key store abilities, meaning it is owned and transferable, and shop ID binds it to one specific shop. For those not as familiar with Move, this leverages the fact that authority lives in the object itself, not in a sender check anywhere. Every admin function takes an owner shop cap as an argument, and if you don't hold that cap, your PTP won't build. And notice in create shop down here, it returns a tuple. Shop and cap are minted atomically, then the caller splits them. So shop gets shared for everyone and cap stays with the owner. Okay, and next we'll talk about the big one, shop itself. The shop struct, it is architecturally the shared root. Within it, there are 3 type tables hanging off the shop's UID as dynamic fields, as you can see here. The interesting one is accepted currencies, keyed by type name, which is Sui's runtime type identity. This design choice allows different currencies like USDC, Sui, and more to each register against a distinct type name. So you get 0 collisions and 0 per currency branching. If you're building anything multi-currency on Sui, this is a potential model. And just to be clear, for currencies, the shop uses type name at runtime to look up which coins are accepted. The phantom T story comes in a little bit later on the receipt side, and it's a separate compile time mechanism. Now let's check out the listing module. Within here, let's scroll up to the actual shop item object. We've seen the owner side of things. What about the buyer? Here's the receipt object. 2 things make this struct interesting. First, it has key and store with no drop ability, meaning it's a linear resource, aka once it's minted and transferred to a buyer, the compiler refuses any code path that loses it. Second, it uses a phantom T. This type parameter tags the receipt with the item type at compile time, but adds 0 runtime bytes. See the Sui Move docs for more details. So with all that said, What that means is that a concert ticket and a digital pass ends up as different types, and anything downstream consumes them by type signature alone. A venue contract that takes concert tickets gets type system as its access gate, and no lookup into the shop is required. How fine-grained that gate gets depends on how many distinct types you publish. Reuse one type across multiple listings, and consumers fall back to checking fields like name at runtime. It should be noted, though, that upon purchasing items within this app, the received object is a receipt, not the item itself. So the item type field carries the type name at runtime, so indexers and explorers can read it, since phantom T vanishes once the code compiles. If you actually need item-specific attributes, though, like a VIN, a seat number, you would mint a separate T object alongside this receipt in the same PTB. Before moving on to the pricing aspects within this app, I just wanted to say that although this project has a capability, shop owner cap, and it's already transferable today as seen within its abilities, it's a bit unstructured. OpenZeppelin has an access package that would help with this. The library ships standardized transfer ownership, renounce ownership, and two-step transfer helpers with consistent events, all audited. If you're starting fresh today, you can use it as a library. Now, let's get into the pricing logic starting in the shop module. Within this, let's go to the buy item function. It's a good place to start for pricing because it's the settlement entry point. It uses two generics. T is the item kind, C is the currency. Oracle comes in by mutual reference. The payment coin gets consumed, and the function hands back the phantom type receipt plus any change. From here, let's go to assert price info identity macro. Here you can see that the Pyth feeds are first-class shared objects on Sui, read by a mutual reference. Before anything else happens, this macro runs an identity check asserting both the object ID and the internal feed ID match what the shop registered for this currency, so there's no room to slip in a fake oracle. Let's look at the diagram to better understand how this app sets up its purchase PTB and keeps prices fresh. The PTB does the security checks with regards to price. Every purchase is one atomic block, right? So step 0 pushes a fresh Hermes attestation on chain. That's Pyth's off-chain service. Essentially, we're getting a fresh price in every PTB in this case here. In step 1, it reads the same price info object, now fresh, and settles the purchase. You can't execute by item against a stale feed, essentially. The update is always the prior call in the same block. So this app isn't trusting the client to refresh. The PTB requires freshest pricing info. In this app, only settlement PTBs carry the Oracle update. Adding a listing, toggling the shop, registering a currency, none of those need a live price, so their PTBs skip the Pyth step. Only buy item triggers it. You can see the remaining details of buying an item within this diagram. Let's go back and look at the code for pricing in the currency module. Within here, let's look at the function conservative price mantissa to continue our price conversation. This project designs for a conservative mantissa. Pyth gives you a price plus a confidence interval, so mu and sigma within the Pyth documentation respectively. We settle on the lower bound though, so mu minus sigma, aka the fresh price minus the confidence. Under volatility or Oracle uncertainty, you can see how this is useful. The shop prices defensively. And so if sigma ends up too wide relative to mu, we abort the transaction entirely. Continuing on in here, if we look up the function quote amount with guardrails, you'll notice something interesting. Throughout the app, there are dual bound guardrails, meaning that the seller sets the caps when they register the currency. The buyer can tighten pricing via overrides in the buy call. They can only tighten it, they can't loosen it. That effectively means that the value is always the minimum, aka the seller's ceiling. Buyers' further restrictions can be passed along accordingly. Finally, with all of this, in terms of the pricing conversation, if we look up the function quote amount from USD cents and scroll down, within this, basically you can see the math functions being used to carry out this pricing. And this is one of the places where OpenZeppelin Math is used. Mul div with explicit rounding up makes things conservative in the shop's favor. Essentially, from that, arithmetic overflow can be handled with an explicit transaction abort, not silent corruption. Every dimension of this, rounding direction, overflow handling, confidence interval, decimal scaling, it corresponds to a specific bug class. The library centralizes the right answers. Now that we've gone through the code, let's get into the actual UI workflows in action. let's switch to testnet for showcasing the transaction flow. You can spin all of this up on your own local host by following the README for the repo. Owner and buyer keys are configured. Simply populate the .env file with your details and follow along. Here you can see, again, that the owner can create a shop. When doing so, that's a PTB calling create shop and share. The move code returns a shop and shop owner cap tuple as mentioned before, and the script shares the shop via public shared object. And the cap lands in the owner address as mentioned. We've already created one shop. Let's take a look at the cap on SuiScan. Here you can see it's owned by my address 0xe99, the owner address that I've used, with the shop ID 0x59 accordingly. It already has listings and registered currencies as well. If we go back, I already have this open showing that. So here you can see the size is 3 for accepted currencies and the size is 4 for the respective listings. We've already loaded listings, but I'll still walk through the process for it. We're connected to my owner wallet already, and so we can see add item within the UI here. We click add item, and within this you can provide the inputs respectively for your new item. And so if we fill out just things here like steak, and in the item type you would put an item type that's already existing in the contracts. So you could put digital pass, for example, and use its respective address. We fill out its price. We say 10 stock, and we apply a discount. There's 2 discounts available that we can apply. It populates everything down here for you to review, and all you have to do is click add listing. What that's doing is calling the contract function add item listing, and that's gated by a reference to the cap. The listing records the type name of T, so it knows exactly what kind of shop item to mint at checkout. Now let's switch over to the buyer wallet, which is my other address, which I already have set up to actually carry out a buy transaction. Now we'll go ahead and buy the Metro bike with USDC with a discount. So my buyer wallet is connected. I've exited full screen just to make sure that the transactions can be seen with the wallet easily. And we'll switch to currency. It's going to fetch the Oracle quote. Great. We'll apply a discount. There's 2 options right now, 10% off on, and we'll go to confirm purchase. We can review the changes here. Great. And the transaction is executed. Basically what happens is the same PTB structure we walked through earlier. Fresh Oracle update, discounted purchases, receipt, and change, both delivered to the buyer in one atomic block. You can find more details on the PTP construction when going through the TypeScript files under domain/core/src/flows and find files like buy.ts where you can see functions like build by transaction. Now that we made the purchase, let's go down here and we can actually see the purchase items as the receipts. So we have the receipt, listing ID, shop ID, etc. So let's go into the details of the object on SuiVision. And you can see here the owner for this object is my respective buyer wallet, which is great. And accordingly, you can see that the name is Metro Bike, which is proper, and everything else looks proper as well. Switch back to the owner and actually remove the listing, and you'll see that the object receipt persists, and it doesn't matter that the shop deleted the listing that it originally came from. Essentially, the shop has no way to retract what a buyer already holds. That property is what makes this pattern hold up under real integrations, tickets, passes, memberships that outlive the listing that sold them. So there it is, a Sui reference build from OpenZeppelin. The repo is meant to be a living reference, so fork it, check out the patterns you need, submit issues, and more. We're excited to continue to build within the Sui ecosystem, and we just rolled out the fixed point math library and more on their way. You can find links to those libraries and this repo within the docs. Give it a try and let us know what you think.